Hello everyone. In this video we're going to talk about the total probability rule, and we'll look at one example on this subject. So total probability rule says probability of event B is equal to probability of B intersection A plus probability of B intersection A prime. And that's true for any two events of A and B. So let's draw a Venn diagram and explore this a little more. So we have this event B, let's call it, and we also have an event, let's say A, somewhere in this sample space, and they have this intersection area. So total probability rule says probability of B is equal to the intersection of B with A plus intersection of B with A prime. So we understand that A prime is this area. Anywhere outside of A is essentially A prime, right? Right, this is A prime, the shaded area. And probability of B is equal to this intersection area, that is intersection of B with A, and intersection of B with A prime. Intersection of B with A prime is here, right? That's part of B that is not intersecting with A, but is intersecting with A prime. And that is true for any two events. Even if they're not intersecting, that's true, because in that case, probability of B intersection A will be 0, because they're not intersecting, and probability of B intersecting A prime is probability of B. So that's true. This is a rule for any two events. But what you can do is you can further expand each of these using the multiplication rule. So probability of B intersection A can be probability of B given A times probability of A. And that is based on the multiplication rule. If you go back a few slides, multiplication rule says probability of A intersection B is equal to probability of A given B times probability of B, and that's coming from the conditional probability. Now, we can further expand any of those two to these two terms, and this is called the total probability rule. And this rule is also applied when you have more than two events. If you have multiple events, probability of B is still going to be probability of B given AI, where I goes from 1 to k, times probability of AI. Here you had two events, so you only had 1 and 2. But if your sample space has a partition that is divided into A1 through AK, and I need to emphasize here that it needs to be a partition, then you can further expand this to multiple events. Let me show this on a Venn diagram so it gets more clear. So let's say you have this Venn diagram, a sample space, and then you have a partition of AI to AK. Basically, imagine a partition. And you remember, partition is a set of events that do not intersect with each other, but they cover the whole sample space. A1 to A7. In this case, our sample space is a partition of 7 events. In that case, if you have an event B, just like here, right, anywhere, and you want to calculate the probability of B, what you can do is, the idea behind total probability rule is to calculate probability of B. You can calculate each one of these pieces, which are intersection areas with A1 through A7, and add them together. You can calculate each one of those separately and add them together, and that would be probability of B. Let's take this area. This is probability of B intersection A3, right? Which you can write it as probability of B given A3 times probability of A3. You can do the same for any of these parts. This is probability of B intersection with A4, and you can further expand it to probability of B given A4 times probability of A4. So that's why when you have even multiple events, probability of B can be written as these intersections areas that you add them together. That's the essence of total probability rule. But you have to be really careful that you need to have a partition. Otherwise, this rule does not apply. If you only have a partition in your sample space, that rule applies. Even here we had a partition because A and A prime forming a partition. They do not intersect and they form the sample space. So let's take a look at one example to see the application of this rule. In this example, it says a steel beam is intermittently subjected to a load of one of 4 magnitudes. The magnitudes of these loads, their associated probabilities, and the probability that the beam fails as a result of these loads are given in the table below. What is the probability that a load causes beam to fail? So looks like here we have 4 different load magnitudes. The probability of that load being used and probability of beam failure if that load is used. So let's call this load 1, load 2, load 3, and load 4. And here you can see that this is a partition because the summation of these 4 probabilities is 1. And these 4 loads do not intersect with each other. If you think of them as an event in the sample space, there is no situation that 2 loads can happen at the same time. So there is no intersection areas between them, and they sum up to 1. So you can think of this is L1, this is L2, this is L3, and this is L4. And I draw that Venn diagram, and each area is proportional to the probability that they have. So that's why L1 is bigger, because the probability of L1 is 0.4. So this is probability of L1, probability of L2, probability of L3, and probability of L4. What are these numbers here? Probability of beam failure. These are probabilities that the beam fails if we use that load. So it's essentially a conditional probability. Probability of failure given that L1 is used. Probability of failure given that L2 is used, and so forth. Now, the question is asking for what is the probability that a load causes the beam to fail. Just a load. So that's not asking you the probability of failure if L3 is used, because in that case you would have the answer. It just says probability that a load causes the beam to fail. We don't know which load is going to be used. That's probabilistic. So the problem is essentially asking us for probability of failure. But we know that failure is an event that has intersection with all these 4. If you want to calculate probability of F, you need to calculate each one of these and add them together. So the first one is probability of F intersection L1. And that is probability of F given L1 times probability of L1. Well, thankfully we can calculate that. because we know the probability of F given L1, we know the probability of L1, so we can calculate that piece. And then you go to the next one. The next one can also be calculated. That is probability of F given L2 times probability of L2. So you essentially need to multiply these and add them together. And that's the total probability rule. So we can write that probability of F is probability of F intersection L1, intersection L2, intersection L3, and intersection L4, and further expand each one of these and then replace them with their numbers. And when you do the math here, you get 0.003. So that is about 0.3% chance that the BIM fails. That's the answer. It's the probability that the BIM fails given all of these information, that we have 4 different loads and probability of them being used and probability of failure given each load.